Welcome to this video on kinematics, where we're going to look at a car that's sliding backwards down a hill while accelerating up the hill. A car is sliding backwards down an icy hill at 9 kilometers per hour, 2.5 meters per second, and the driver hits the gas. 15 seconds later, the car's displacement is 12.5 meters further up the hill from where it was at time 0 seconds. A. What was the car's average acceleration over the 15 seconds? B. What was the car's total displacement backwards before it started moving back up the hill? And C. What was the car's total distance traveled over the 15 seconds? Before we find the car's average acceleration over the 15 seconds, let's start part A by listing our variables on the left-hand side and drawing a diagram on the right. At time t is equal to 0, our car is here on the hill. 15 seconds later, at time t is equal to 15 seconds, our car is here on the hill. These two cars are a distance 12.5 meters apart. Our car has an initial velocity backwards at minus 2.50 meters per second. That's our velocity initial. Our velocity final of our car is unknown. Also, the acceleration of our car is also unknown. So listing our variables, we have a VI equal to negative 2.50 meters per second. This is because the car is moving backwards down the hill, and we're defining up the hill as positive. We have a time t is equal to 15.0 seconds. We have a displacement of the car equal to 12.5 meters. Our acceleration is what we're looking for, so it's unknown. And we can also note that we do not know our velocity final. You don't have to write it down because we're also not looking for it. We're ready to look at our kinematic equations and find an equation that has VI, T, D, and A in it. Because we're not looking for VF and we don't have VF, we can immediately cross out all the kinematic equations that have VF in them because we know these won't work for us. This leaves us this kinematic equation to solve this problem that has VI, T, D, and A in it. So let's write that down. The displacement is equal to the velocity initial multiplied by the time plus 1/2 the acceleration multiplied by the time squared. Bringing in our numbers, we have D equal to 12.5 meters. This is equal to our VI, which is negative 2.5 meters per second, multiplied by the time, which is 15 seconds, plus 1/2, multiplied by the acceleration, which is our variable we're looking for, and multiplied again by the time squared, which is 15 seconds squared. Now we're ready for some algebra. Negative 2.5 multiplied by 15 is negative 37.5. Our seconds cancel with our seconds, so we're left with just meters. Plus our 1/2 A. 15 squared gives us 225 seconds squared, which is equal to our 12.5 meters. 1/2 multiplied by 225 is equal to 112.5. So if we rewrite this all, we end up with 12.5 meters is equal to negative 37.5 meters plus 112.5 seconds squared. And this is still multiplied by our acceleration. To get our acceleration all alone, we start by moving out the 37.5. So we add 37.5 meters to both sides. On this side, our negative 37.5 cancels with our positive 37.5, and on this side we end up with 50.0 meters is equal to what we're left with here, are 112.5 seconds squared multiplied by our acceleration. And now we're ready to get our acceleration all alone. Our acceleration is being multiplied by the 112.5, so we have to do the opposite. So we divide both sides by 112.5 seconds squared. And on this side it cancels out, leaving us with just our term for our acceleration. And this is equal to 0.4 repeating decimal meters per second squared. So we write this to end this question as 0.444 meters per second squared, which is equal to our acceleration. We can just get our units from right here, meters per second squared. And before starting part B, we can add our acceleration to our list of variables, 0.444 meters per second squared. In part B, we look at what was the car's total displacement backwards before it started moving back up the hill. We could adjust our diagram, but it might start getting a little convoluted. So let's just make a new diagram for part B. In part B, our car initially starts on the hill with a velocity of negative 2.5 meters per second. It then slides backwards, so we're trying to find the total displacement backwards before it starts moving back up the hill. And right before it starts moving back up the hill, we have a velocity final equal to 0 meters per second. What we are trying to find in part B is this displacement here backwards. And throughout this entire motion, our car has an acceleration up the hill equal to 0.444 meters per second squared. So summarizing this diagram, our car has an initial velocity down the hill of negative 2.5 meters per second. The driver immediately hits the gas, so the car is always accelerating up the hill. So initially, how fast the car is sliding down the hill decreases until it finally hits 0 meters per second. At that point, the car starts moving back up the hill. But our question ends once we hit this velocity final of 0 meters per second, because we're trying to find the displacement backwards from when the car starts sliding backwards to when the car stops sliding backwards. Now we need to adjust our variables accordingly. Our VI is still negative 2.50. This is the velocity the car starts to slide backwards at. Our acceleration is still 0.444 meters per second squared. It's the acceleration of the car up the hill after the driver hits the gas. Our velocity final in this question is 0 meters per second. This is the point where the car stops sliding backwards. Our time of 15 seconds and our displacement of 12.5 meters are both from part A. We're no longer looking at the time and displacement of the car moving up the hill. We're looking at how far it travels backwards. So our displacement here is the new variable we're looking for. We are now ready to pick our kinematic equation. We're looking for an equation that has VI, D, A, and VF. We don't have, and we're not looking for T, so we can cross out all the equations that have T in them. This leaves us with this kinematic equation, so we can write it at the top. Velocity final squared is equal to velocity initial squared plus 2 times the acceleration multiplied by the displacement. Now we can add our numbers. Our velocity final is equal to 0. Our velocity initial is equal to negative 2.50 meters per second. And this entire term is squared plus 2 multiplied by our acceleration, which is 0.4 repeating decimal. Let's use our unrounded number from part A. That way we don't introduce any rounding errors. And our units here are meters per second squared. And this is all multiplied by the displacement that we're looking for. Negative 2.5 squared is equal to 6.25 meters squared per second squared, because the unit's square as well, plus 2 times our 0.4, which gives us 0.8 repeating decimal meters per second squared. And this is all still multiplied by our displacement, d, and equal to 0. We're looking to get our displacement d all alone, so we start by subtracting 6.25 from both sides. So on this side, our 6.25 minus our 6.25 cancels out. And on the left-hand side here, we get negative 6.25 meters squared per second squared is equal to our remaining term here. So 0.8 repeating decimal meters per second squared multiplied by our displacement d. And finally, to get our displacement d all alone, it's being multiplied by 0.8, so the opposite of multiplying is dividing both sides by 0.8 meters per second squared. And negative 6.25 divided by 0.8 is negative 7.03 meters. On this side, these two terms cancel out, and we're just left with our displacement d. Let's just confirm our units quick. Here we have meters squared over second squared divided by meters over second squared. So one of our meters on top cancels with our 1 meters here, and our second squared cancel with our second squared, leaving us with just our meters term. Our negative sign here makes sense. We initially defined our positive acceleration up the hill, so we defined up the hill as positive. Similarly, with our velocity initial, which was negative, we defined this as sliding down the hill. So our displacement down the hill is in the negative direction. We can add this displacement backwards into our variables, so we have it for part C, negative 7.03 meters. In part C, we're asked, what is the car's total distance traveled over the 15 seconds? What this question is really asking is, do you know the difference between distance and displacement? We already know that the car's displacement over the 15 seconds is 12.5 meters. To find the distance over the 15 seconds, it's easiest to just draw a quick diagram again. Here's our car at time t is equal to 0 seconds. We know that the car initially slides backwards down the hill a distance of 7.03 meters, like we found in part B. We're told in the question that after the full 15 seconds, the car is 12.5 meters from its starting point. So that would be 12.5 meters from where it starts at t is equal to 0. So here at t is equal to 15 seconds, the car is 12.5 meters from its starting point. So if the car goes backwards, that's a distance of 7.03 meters. We then know that the car also has to travel forwards back to its starting point at t is equal to 0 seconds, which is another 7.03 meters. And then it travels another 12.5 meters up the hill. We can sum this all up to get our total distance traveled by the car over the motion. So we know that initially our car goes backwards 7.03 meters. The car then travels back up the hill to its starting point at t is equal to 0, another 7.03 meters. And finally, the car travels another 12.5 meters up the hill, giving us a total distance of 26.6 meters for the entire motion backwards and back up the hill. Thank you for watching this video on kinematics of a car sliding backwards down a hill while accelerating up the hill.